Okay, welcome everyone. In this video, what we're going to be looking at is shear and moment diagrams using principles of integration and what I call the graphical method, or looking at areas and slopes. This is what a shear and moment diagram looks like. I have a sample beam shown here with this 1 kip per foot over 10 feet, a concentrated load of 2 kips, and a 3 kip load on the end. And if I look at what the shear diagram and moment diagram would look like, I see examples of those down there, and they tell us a lot of valuable information, such as in the shear. I see that I have a maximum shear of 7.25 kips, and I can kind of see how it changes throughout the beam, right? For the moment, I see I have a max positive moment of 26.28 kip feet, max negative moment of negative 15 kip feet, and that could be beneficial if I were putting in rebar in a concrete beam, or if I were designing the depth of a steel beam, or various things. We would want to know these values of what the shear and the moment are along the beam. Or if I had a little crack in here, right? That's a classic. A little crack in the beam. Hey, a little crack in the beam, I can come down and say, oh, well, at that time, I know what my shear and what my moment were. So before we get into that, I want to spend just a second and talk about sign conventions. What is positive versus negative when we talk about these bending moments and shear forces? And it does depend on if you're looking at the left-hand side of the beam or the right-hand side of the beam. I'm generally going to be working from the left-hand side to the right-hand side, which means I have a positive shear, which points down, and a positive moment that points counterclockwise. Now, if you were analyzing the other side of the beam, like working from right to left, and I did any kind of section in there, I'd have a positive shear pushing up and a positive moment going clockwise. The easy way to remember the moment is what overall effect is it having on the beam? Is it making the beam want to smile? Meaning, is it making a compression on the top and tension on the bottom? So both those moments would be doing that. So both those moments would be positive. So hopefully that makes sense. So this whole method is based on the relationship between load, shear, and the moment. And this relationship basically looks like this. The change in my shear as a function of x is equal to negative of my load. And I can rearrange this equation, integrate both sides, and end up with the integral of dv is equal to the integral of negative w dw. So what that gets at, or what we can do with this, is what this is telling us is the change in our shear will be equal to the area under our load, distributed load. And the other equation that we're going to be deriving from is the fact that we know our change in the moment with respect to x is equal to our shear. Or same idea, can rearrange this, and I end up with the integral of the change in moment is equal to the integral of v, my shear, with respect with x. So what that tells us is that the change in my moment is equal to the area under my shear diagram. If we look the other way too, we can see these relationships between slope, shear, and also the slope of our shear, and what that looks like for our load. And there's a little foreshadowing. We can kind of see how that would work if I have something with a flat load, a flat evenly distributed load. Or I guess evenly distributed load by definition would be flat, right? Then I end up with a line with a constant slope, basically integrating. So summarizing what that looks like, if I were to start with something like a concentrated load and call this my loading W, the overall shear would look something like this. It would come up, over, down, over, up, assuming this is a simply supported beam, right? So that is my shear V, and my moment. This gives you a general idea of what these shapes will look like as we move from one to the other. We'll see this in an example in just a second. But what I see here is that as I move from top to bottom, what I have is an increase, and I can do the same thing for an evenly distributed load. And if I were to look at the shear, it goes like that. So like I said, we're increasing in power. So like, for example, if this W is equal to 3, a constant 3, maybe it's 3 kilonewtons or 3 kips or something. Here my shear would be equal to minus 3x. Of course, you do have this little bit here for our reaction. We'll talk about that in a little bit. But in general, as far as the shape, we're at a flat line, then we're at a linear line where we have a slope of 3. and my moment would be equal to minus 3x squared over 2. So we end up with some quadratic squared function. So that's kind of the principle behind these shapes, is understanding what they look as from going from one to the other, and then understanding this principle of areas. I think it'll make more sense in an example, so let's take a look at an example. All right, so for this example, we have a 20 kilonewton concentrated moment, 8 kilonewton concentrated force, and a 15 kilonewton per meter distributed load. This is about as hard as they get, I think. So a little bit of everything going on. So I like to work over here, and that gives me room to draw my shear and bending moment diagram right below the beam. So the first step that I'm going to do is I'm going to solve for my reactions for this beam. Boom, just like that. Not going to spend much time talking about that because that should all be reviewed. What I find is I have 67.3 kilonewtons acting at B, pointing up, and at A, I'm pointing down at 14.3 kilonewtons. So after I have my reactions, the next step, step 2, is that I want to draw some reference lines to draw these shear moment diagrams. And these reference lines will be at what I like to call interesting points. Now, technically, what these interesting points are discontinuities with some kind of shear or moment functions. And those would occur at any kind of reaction, at the beginning or the end of a distributed load, or at any concentrated forces or moments. So, and it makes sense when you come up here, you're just drawing a line anywhere where there's something that looks like something might be happening. So I have a concentrated moment up here, I'll draw a line down for that. I have this force of 8 kilonewtons, and I have my reaction, and then I have my end of my distributed load. So those are all my important lines. This is where I'm going to be drawing my shear force and put my unit on here of kilonewtons. And below that, I have my moment with the unit of kilonewton meters. So the way I approach this is I start with this 14.3 kilonewtons, and it's pointing down. And so immediately what I do on my shear diagram is I just go down 14.3, and I put negative 14.3 kilonewtons. Then I work my way from left to right. I come over here to that 20 kilonewtons. I say, what's that overall effect on the shear? There is no effect on the shear to that 20. It's a bending moment. So I just keep on trucking and keep on going along. And then I'm pushing down with an additional 8 kilonewtons. So negative 14.3 minus another 8 brings me all the way down to minus 22.3. And then I continue over, and I hit this 67.3 pointing up. Well, if it points up, I'm going to go up 67.3 from this negative 22, and that brings me up to a positive 45. Now the last step, probably the hardest, is when we were saying what's the area. The area under distributed load is equal to our change in our shear. Well, the area is 15 times 3. It's pointing down, so we're going to say negative 45. So I start off with a positive 45, go down to negative 45, and that's it for my shear diagram. Now my moment diagram, I have a bunch of areas I can look at. So I like to start by saying, well, what's my area underneath these different shapes in my shear diagram? Well, I have this, the first little rectangle, this little rectangle right here. The area of that rectangle is minus 14.3 times 2, which is negative 28.6. I'll circle it, know it's an area. Then I have this second little rectangle in here. That would have an area of minus 14.3 times 1, which is minus 14.3. Then this third rectangle, I have an area of 2 times negative 22.3, which is negative 44.6. My last triangle shape, I have an area of a triangle 1/2 the base times the height, 1/2 times 3 times 45, gives me a positive 67.5. So when I move down to my moment diagram, I start at the very end and I say, is there any kind of moment over here? Well, there's no moment. In fact, there's a pin, so it's free to rotate, so there can't be a moment there. Because there's no moment, I'm starting at 0. And I say, well, how much do I change as I move from segment? Well, that's equal to the area underneath my shear curve. So I'm changing by this negative 28. So I have to get down here to minus 28.6. So I know I'm starting at 0. I have to get to minus 28.6. The next question is, how do I get there? And this is where I use this idea of my relationship moving up by increasing by power, right? So if I have a flat line, the next power up would be some linear slope. So it's like that, you know, I guess it would be kind of like this example right here where I'm a flat line, I'm a linear slope. Or slope of the constant, well, whatever, you know what I mean. So after I get to that point, now I have a concentrated moment of 20 kilonewton meters. So I have to figure out what to do with that 20 kilonewton meters on my moment diagram. So it's either going to go up to 8.6 or it's got to go down to negative 48.6. So the idea is I have to figure out if this is a positive or negative 20 kilonewton meters on this beam. And how do I know? Well, I have to think, what does it do to the beam? Is it making the beam smile or frown? And these internal moments can be a little tricky when you first look at them, but we're working from left to right. So if I were to twist that beam and think about what the deformed shape looks like, it would look kind of like this, right? Meaning if I'm twisting it, that 20 kilonewtons, I would have the right-hand side going down immediately and then coming back up at B. Well, this is the side I'm concerned with as far as the smile versus frown analogy. So this is making it smile, which means it is a positive 20 kilonewtons. So I'm going to go up on my moment diagram 20 kilonewtons, bringing me to minus 8.6. Then I have this negative 14.3. So negative 14.3 added to this negative 8.6 brings me to negative 22.9. And then I have a negative 44.6, so I'm going even further down. Well, should be slightly steeper, it looks like, right? And that brings me to negative 67.5. Now my last area is a positive 67.5, and that usually is an indication that I did something right, because I'm ending up at 0. There is no external moment here to bring me to 0, so since it closed up, it means I probably did something right. So I know I have to go from negative 67 up to 67. I have to say, well, how am I going to get there? So this one I actually have some, now I have a line with a constant slope. I'm going to have some sort of parabolic function, right? But I have to figure out if it's going to be concave or convex. You know, is it curved up or curved down? And the way you can think about this is the derivative of my moment is my shear, meaning this distance here is actually what my slope is. So my slope is 0 at the end, and it's becoming more and more positive as I move from the well, I don't want to really move from left to right. I guess from the 45, I'm at a very positive slope, meaning I'm pretty steep, and then it approaches 0. So this is actually the direction it's going. And you could fill in the lines, whatever you want to do at that point. We could also identify our maximum moment to be negative 67.5, max shear 45, so on and so forth. So hope you found that helpful, and I look forward to talking to y'all soon. Thanks.